Welcome back, everyone. Here we start the second third of our course. This is lecture number 30. We're going to start talking about waves, electromagnetic spectrum again, and interference, and a bunch of different things. So let's take a look. First, we're going to define a wave, and this is a generic type of introduction, okay? Periodic disturbances, a back and forth change of some kind that is repeated regularly as time goes on, that spreads out from a source and carries energy with it. Most important that you realize that waves carry energy, okay? We'll talk more about that in a bit. All right, three different properties of waves we're going to discuss today. One is diffraction, the second is refraction, and the third is interference, both constructive and destructive. And we'll see if we get to the two types of waves today, transverse and longitudinal. All right, first let's begin with our discussion of diffraction. Okay, what is diffraction? Well, here's my example. Imagine I'm on a street corner and I yell for my friend Vito, Vito! The waves propagate, but you see they also bend around the corner, and Vito, that's Vito, can actually hear the waves. Now, I'm going to keep using this uh, waves versus bullets. Suppose I tried to shoot Vito. He's not a nice guy. But suppose I tried to shoot Vito. If you look, my bullets go straight. Bullets do not bend around a corner. This bending around a corner or bending around an obstruction is called diffraction. Waves diffract. Bullets do not diffract. Okay? Here's another example, water propagating. There I am hanging out. Here's water coming in, hitting a barrier with a hole. Okay, there's a slit. As the water propagates outward, it spreads. Waves spread out. Once again, there's my bullets. If I shoot bullets, bullets do not spread out. So bullets go straight, waves propagate out and bend around this obstacle. And there's Vito again, and he gets hit by these waves. So the waves propagate around an obstacle. So that's diffraction. Okay? Very simple idea. Waves diffract, particles do not diffract. Okay. Second thing, let's talk about refraction. Refraction. Okay. Here's where waves bend when passing from one medium to another. You know, when it goes from, say, air to glass or glass to air or water to air or whatever. Those are mediums, different mediums. Okay. I want you to pay attention that the frequency of the waves do not change. And I'm going to give you an example here of what refraction is. Now, you've all seen it. Somebody drinking a glass of 7 Up or something, and the wave looks bent, the straw looks bent, or somebody's feet in the water and they look at a funny angle. Okay, first let's talk about suppose we have water, and suppose I drop a pebble. As I drop a pebble, you see these waves emanating outward. And these lines I've drawn with the arrows, these are called wave fronts. The wave fronts propagate. And if you go far enough away from where you've dropped the stone, these wave fronts look almost flat, like straight. Okay, as you go far away, the curvature is much less. All right, so now let's talk about an army marching. Okay, and I'm going to think of this army marching as wave fronts. Okay, these are my wave fronts here. Okay, wave fronts. Almost exactly straight, as if these wave fronts were far away. So this is the top of the heads of soldiers marching. Okay, now marching. Now I'll tell you an old story from 50 years ago, more than 50 years ago. Had a friend, Vinny, big strong guy, big Vin, but very heavy. And you know, this is the time of Vietnam War. And Vinny, I don't know why, decided to join the Marines. So Vinny joins the Marines, and I get to see him 6 weeks later after basic training. It's big Vinny. I go, Vinny, you look amazing. He's muscular, looks in great shape. I go, Vinny, it's just incredible what happened. And he says to me, well, you know, that was really hard training. And I said, Vinny, what's the matter with you? Well, it was tough. I go, Vinny, what's wrong? He had no teeth. I goes, well, I said something, and the sergeant punched my teeth out because I didn't listen to him. So the point is, when you're in the Army, you'd better listen, or the Marines, or you're going to get your teeth punched out. So you got to listen. Now, when soldiers march, hop, 2, 3, 4, 1, 2, 3, 4. The Army thought they won the war, but the Navy won it a year before. That's a cadence, and that's the rate at which you move your feet. So for us, if we're using the analogy of waves, that would be the frequency. So the frequency does not change. You do not change the way you're moving your feet. You must move them like that, or you will be talking like Vinny, okay? So you want to talk like Vinny. So what happens when this army marches, the wave fronts hit, say, a muddy river? Now remember, your feet have to move at the same frequency or you talk like Vinny. If you look at the soldier on the bottom, they hit the muddy river first. What happens when they hit the muddy river? Again, their feet are moving at the same frequency, but now they're not moving as fast because they're in the mud, so they're moving like this, but they're moving slower. The people at the other end of this wave front up here are still on dry land, so they move faster. And so the net effect is that this wave front bends. The wave front bends. When it goes back out, everything catches up. So here, the wave front bends because only at an angle. If it was straight, nothing would bend. This guy hits the mud first, slows down, and this one bends because it catches up because it's in the other medium. So that's essentially what refraction is. It's waves going from one medium to another. I want you to notice that waves can slow down or speed up when they go to a new medium. So if the speed changes, the wavelength can change, but the frequency does not change. Okay? So let's keep that in mind. All right, let's look here. Let's go and talk for a bit. Let's talk for a bit about interference, okay? Constructive and destructive. Okay, excuse me. Okay? Well, again, the ideas are very, very simple. All right? If I have a wave propagating, okay, we'll talk about wavelength and all that stuff soon. There's a wave propagating. Listen to my words. If I have a second wave in phase, do you understand? In phase. In phase means when that one's a maximum, that one's a maximum. When this one's a minimum, that's a minimum. So they're identical waves, one laid on top of the other. If you add two waves in phase, you get a bigger wave. That's called constructive interference. Very simple. The waves are in phase, you get a constructively bigger resultant wave. Okay? Again, if we have a wave like this, and we have a second wave now out of phase, what happens? This is a max, that's a min, that's a min, that's a max. They cancel each other out. So you get nothing. So out of phase, when they're out of phase, this is destructive interference. And where in phase, it's constructive interference. Okay? Now, we learned in a couple of lectures ago about electromagnetic radiation. Well, electromagnetic radiation behaves like a wave. Okay? So imagine the lights here or the sun. Would you say that the light from the sun, coming from the sun, is constructive or destructive? Okay. Well, the answer is it's a mishmash. That's a silly word, but I'm going to write it here. A mishmash. A mishmash just means that it's constructive and destructive all mixed up. Okay? What would happen if a wave was completely constructive? All right, let's see. Well, if light was completely constructive, watch. Now what I said was a mishmash, it would look like this. There's a wave, there's another wave, there's another wave, there's another wave. That's a mishmash. It's like when people jump into a swimming pool, the waves are all sometimes big, sometimes small, sometimes nothing, all wish-washy, okay? Or you can just touch the water and make all the waves, like in a bathtub, go all in phase, and then the amplitude gets very, very big. Okay, so this is a mishmash. But suppose you had light or any type of wave, but let's talk about light for now. And there's a wave, and there's another one exactly in phase, and a third in phase, and a fourth in phase, and a fifth in phase, and a million things all in phase. What type of wave would you get? Well, you'd get a wave that was super, super strong, super powerful. If this is light, if everything's in phase, we call this a coherent light source. Okay? A coherent light source, an example of a coherent light source is a laser. Everybody's seen lasers that can cut through metal or glass or all these things. We have lasers at the checkout counter at the grocery store and so forth. So a laser is a coherent light source. Everything is in phase. How do you get it to have all the waves in phase? Well, you have to make a laser. It's very complicated. And who wrote the equations for a laser? Albert Einstein in 1918 or 1919, something like that. And they weren't able to build lasers till the 1960s. So coherent light source is a laser, all the waves in phase. Okay, in general, most light, most things are mishmash. They're just a mixture. And so it's not that powerful. What would happen if the sun was a laser? Well, there'd be no earth, right? We'd be zapped and vaporized and all that stuff. Okay, so let's see, what else? All right, let's talk about, so we talked about interference, refraction, diffraction, constructive, destructive. Okay, let's talk for a bit about the two types of waves. Okay, the first type of wave we're going to talk about is something called transverse wave. Okay, oops. Imagine you have a string. Okay, imagine you have a string going across the room. And suppose I wiggle it. I'm going to wiggle the string. Okay, so I want you to watch. This could be like a guitar string or violin string. So I'm just going to put a string like this. And then I'm going to pluck it, just like you pluck a guitar string or you pluck a violin string. So here I'm going to go this. And there I plucked it. You see, it's moving with a velocity v. A few seconds later, perhaps, that wave is propagating. Can everybody see that? It's propagating. A little bit later, still propagating. A little bit later, still propagating. There's my wave propagating. So now I have a question. Remember, this is just a string that I've plucked. Suppose I put a red dot on here. Okay, this is my red dot. It's a red dot painted on the string. What happens to this red dot as the wave goes by? That's my question. In other words, what direction is the disturbance? Now, let's look at this. In which direction is the wave moving? Well, you can see the wave is moving from my left to right. The wave is moving that way. But what happens when the wave hits this red dot? Which way does the red dot move? Does it move to the right? Does it move to the left? The answer is no. What does it do? It moves up and down. Okay? So we see that the wave is propagating this way, but the disturbance is up and down or perpendicular to the direction of motion. So in transverse wave, TW, transverse wave, is a wave where the disturbance is perpendicular to the direction of motion of the wave. So again, the wave is moving that way, but if you put a dot on it, the dot moves up and down. So the disturbance is perpendicular to the direction of motion. This is called a, a transverse wave, and a perfect example, write this down, of a transverse wave is electromagnetic radiation. As we'll see, electromagnetic radiation has, remember, wiggling electric fields and wiggling magnetic fields. They're both perpendicular, and then the wave propagates at a direction perpendicular to both. Okay, so electromagnetic radiation is a great example of a transverse wave. Now, I just want to talk about the string for a second. Okay, can everybody see? The string is propagating. Now suppose I put a slit. So the string goes through a slit. Okay, it goes right through the slit. Now imagine I pluck the string. So the string is propagating up and down. So there's my string and there's the propagation going. So now it's going to hit this slit. What happens to that wiggling going up and down? Well, if my slit is like this, it wipes out that wiggling, the disturbance. If my slit is like this, the wiggling gets through. But if I put it like this, it doesn't get through. If I put it at an angle, part of it gets through. Okay? When I do this, this is known as polarization. Polarization. So transverse waves may be polarized. Perfect example is your eyeglasses or your sunglasses. What are sunglasses? Well, electromagnetic radiation is wiggling this way and this way, in all different ways. It's a mishmash, okay? When you wear sunglasses, that means there's slits. Let's say the slits are going like this. If the slits are going like this, it means the only thing that gets through is stuff wiggling like this. Anything with components going perpendicular get wiped out. So anything going like this gets wiped out. So a polarizer or your polarized sunglasses have little slits and it wipes out half of the radiation. Okay, only stuff going like this. Okay, if I then put a second polarizer like this, then nothing would get through because the first one only allows this stuff, and then the wiggling stuff would hit this way, and then nothing would get through. So if I had broken sunglasses, which I usually have, and I put them together and rotate them, if I rotate them at right angles to each other, if they were perfect sunglasses, no light would get through because they're polarized. So polarization is a property of transverse waves. Okay? Very good. Talk about longitudinal. Check. Let's talk about longitudinal. A longitudinal wave is a different beast. Okay? Longitudinal. Okay? So let me give you an example. Let me show you. In the last case, for transverse waves, I put a string across the room. Here, I'm going to put a spring. Okay? So here's a spring. Stretched just across the room. Now suppose I push on the spring. If I push on it, there'll be a little bit of compression. So I'm going to draw it like this. And I'm going to draw it very dark there. Excuse me. And then as we go on, that dark smushing is propagating. You see this thing is propagating. Okay? And then a little later, The smooshing is propagating. Okay? Once again, if I put a red dot, you could put blue, it doesn't really matter. If I put a red dot or some painted mark on this spring, then the motion of the wave is again left to right, right? Going this way to that way. Now, which direction does the dot move? Well, when the wave propagates there, the dot does not move up or down. It moves parallel or anti-parallel to the direction of motion of the wave. So in a longitudinal wave, LW, okay, disturbance is parallel, I'll put in parentheses, or anti-parallel to the direction of motion of the wave, to the motion of the wave. Okay, so this is a slinky. That's all I've done, right? Today, you kids have Xbox and all these toys and three-dimensional things and everything. When I was a kid, what do we have? We had a spring, and this is what we do for a couple hours. Wow, look at this. Oh, isn't that? And then some genius realized that this spring could go down the stairs, and we'd watch that for hours. So, okay, boomer, now you know why we're crazy. We watch springs all day. All right. So a longitudinal wave is a disturbance where the motion is parallel. Disturbance is parallel or anti-parallel to the direction of motion. So my question to you is, can longitudinal waves be polarized? Now remember what polarization was. I have a slit and the wave, part of it got canceled out. It was wiggling. Now if I have a slit and I have my spring going through there, don't take this the wrong way. If I have my spring going and it's oscillating, you see that longitudinal waves may not be polarized because the direction of motion is parallel or anti-parallel. So having a slit doesn't do anything to the wave. Does everybody see that? Okay, so longitudinal waves may not be polarized and transverse waves may be polarized. All right, we discussed everything here. So in the next lecture, we'll start talking about the mathematics of waves, and I'll draw a picture and talk about wavelength and frequency and do some problems with electromagnetic radiation and review the electromagnetic spectrum. All right, see you soon. Be safe.